All right. Thank you very much for hosting. This is Alan from Brevis. I'm very excited to talk to you about our recent work on modular and performant zkVM called Pico. So we all know that blockchains are world computers. They're decentralized. That they have like so many great properties. But the thing is, like, if every computation is going to be happening on chain, it simply cannot run faster than a single server, right? It's single server. It's just a centralized. It's just can handle the same computation as the blockchain, right? And the way to actually scale the blockchains up is to do the off-chain verifiable computing, which means like for the blockchain, it handles all the computation. Whenever we want to do the kind of computation, complex computation, we offload this kind of complex computation to Brevis. So this is exactly what we do. And then after that, we have several toolkits, modules to compute the corresponding results, as well as generating a ZK proof and send it back to the blockchain. So we can basically verify it on chain and then use the proof, use the computation results trustlessly. So this is what we call the smart off-chain verifiable computing, and it is useful to massively scale the throughput of the blockchain. Okay, so we have our first product launched last year, which is our on-chain data access ZK coprocessor. So it's actually generating a ZK proof of arbitrary computation on any historical on-chain data. So whenever any kind of project want to access some kind of on-chain data, it can use make use of our ZK coprocessor and query it, and we will return it the results, historical data, as well as the corresponding ZK proof for it to be used. So we have already integrated with many kind of our partners, like PancakeSwap for their volume-based rewards. There's also usual the rising star of the stable coin for their continuous incentive plan, all this kind of stuff. So this is just a partial list. There's many more that is coming. So in this way, they could use the computation results on chain in a trust-free way without just directly computing all the complex logics on chain, right? So basically, this is what we do for the data access, but off-chain verifiable computing can go way beyond just the data access ZK coprocessor because we may have different logics, right? We may have like more complex business logic. We may want to prove some kind of like real-time Ethereum blocks, directly send it to the on-chain instead of directly using the computation of the EVM. We can also have the zkVM, the verifiable AI inference, where we can attest the integrity of the model. It is basically impossible to host a model, AI model, on chain because it's just too large, and it's impossible to do that. So the summary is that we need to support generalized computing to democratize ZK. And then there are basically two approaches for that. One is the ZK coprocessor, as we did in Brevis, the first project. The benefit of it is blazing fast, so that we can just use it directly. But the thing is, like most of these kind of ZK coprocessors, they are handwritten circuits, right? So they are sometimes very application specific, so that they do have the limited generalization. And also, since you have to deal with the handwritten circuits and you have to write out your handwritten circuits, it's sometimes for developers it's kind of tedious to use it. There are the other series of solutions called zkVM. It's highly flexible because it just requires the developers to develop the plain Rust. They can just write the plain Rust into the logic, and then it's very easy for them to deploy and develop. But the thing is, like, comes with a huge cost of the performance overhead. So this is the pros and cons of the two different things. So to summarize, we basically want to have a balance between developer time, security, cost, performance, and so on. There are many things to balance over. And then different projects may have different priorities here. There's also one thing that I didn't mention before, is that we need this solution to be adaptive towards faster evolving ZK theory. So since there's a proposal in 1980, the ZK theory has been developing at a very fast pace, especially for these 4 years, where it has been finding many kind of applications in different projects. So we can see that newer ZK theory, ZK protocols are proposing every year. every year, and we want our protocol or our zkVM or zk coprocessor to make use of it. That is to say that either zkVM or zk coprocessors, a one-size-fits-all solution will be inherently limited. All right, so takeaway is that a good solution is to be performant. It should also be developer-friendly. So we can see that zkVM and the zk coprocessor are basically trading off between these two factors. And the third factor is being flexible and being future-proof is usually ignored by any of current solutions. So what we do at Pico is that we try to answer the best way to balance all of these things into a one zkVM. So the Pico is pretty flexible and future-proof. It has its modular structure so that we can change its proven backends pretty easily. We now have different proven backends that is supported, and you can just change it with one line of code. It is also customizable in proving workflows. So for different applications, we have different workflows for the zkVM, and it is highly customizable and easy to just do the plug and play. It is also pretty performant. It's not only because it is modular, it has like a pretty good circuits written, but also because it is offloading very heavy computations to zk coprocessors. There are two types of zk coprocessors. One is the function level zk coprocessor, which is also known as precompiles. These are just cryptographic hash functions like catcheck, Poseidon 2, so on and so forth. These are usually done by all the other zkVMs as well, but there are other things called application level zk coprocessor, like the Brevis data access zk coprocessor, which is a huge set of SDKs, circuits that is very application specific. And by integrating these kind of things together, we were able to achieve the best performance. It is also developer friendly because it's just simply a zkVM. You can just write plain Rust. And no matter how large is the program, it can help you just do the chunking of the huge program into several pieces. This is called continuation, and Pico directly supports that automatically. Okay, so this is some of the showcase here. It is designed to be flexible in proving backends. For now, we have been supporting 3 proving backends. The Stark on Koala Bear, which is our default, Stark on Baby Bear as well, which is also used by some of the other projects, and the Circle Stark on Modular 31. So Circle Stark is pretty recent, and we are happy to integrate it as a more advanced theory for our proving system. And then there's also trade-offs between Starks on different views. One is Koala Bear and Baby Bear. Since they do have different 2 acidity, Koala Bear has 24, Baby Bear has 27, but it doesn't really matter since we already automatically support a continuation. So it is fine to directly use Koala Bear. And besides that, Koala Bear does have advantages over Baby Bear because it can prove the Poseidon 2 hash function blazingly fast compared to Baby Bear. So it has its own advantage, which is why we set it to be default. And then on the right, you can see that just setting a client to be having the proving backends of, say, either Koala Bear, Baby Bear, or Modular 31, it's just a one line of code. All the other things, all the other APIs stay exactly the same. So you don't have to change your code at all. So imagine that you have some kind of application circuits that you want to test it out. Then you just do the run and the switching different proving backends to see which one fits you best. It is also pretty highly customizable because it has a pretty flexible proving workflow. So the first thing is that it will transform, the whole workflow works as follows. So originally we have a RISC-V program. It is translated into a RISC-V proof by the RISC-V instance. And then it is converted into a recursion proof or several recursion proofs because we are supporting a continuation, and then the program may be very large. So we have like several proofs. And then we go through the combine phase where several proofs are recursively proved to be and then combined to be a single proof, right? And after that, we have this compress, embed, EVM, which ultimately translate the final proof into a constant-sized on-chain verifiable proof. And then all these kind of modules can be plug and play. So you just, for some of the applications, you don't need the combine phase, then you just take them out. For some of the things you don't want to do the compression, then you just take it out, or adding another phase of compression. It is kind of easy to just add it or delete it. Okay, so Pico is by far the fastest zkVM on CPU. So we have compared, again, benchmarking compared to RISC-0, OpenVM, the SP1 as well. And then we also benchmarking on different workloads, ranging from smaller artificial ones like Fibonacci program to more real-world cases like 10-minute light client, or to prove an Ethereum block of number 171.06222, written in Wraith. And we benchmarked them on an AWS server, and there's basically no optimization made on compiler for all of them, because some of them may require different kind of compiler, which makes the comparison not apple to apple. So to make a fair comparison, we just use their plain code without any compiler optimization, and then with just their direct, their default parameters to be used. And then it turns out that for all of these workloads, we are at least 70% faster compared to the second best among all of the other variants. Okay, so hopefully I have already convinced you that Pico itself is already very fast. And then it actually goes beyond that, because Pico now is pushing the modularity to a new level. For all the other zkVMs or existing solutions, they are based on this RISC-V ISA, and then they are integrating the function level pre-compiled of zk coprocessors, like CatchX, SHA-2, and something like that. But Pico goes way beyond that. It is able to, and it's kind of easy to integrate the application level coprocessors, like on-chain data availability or access zk coprocessor, zkML as well. We also have some kind of zkML module as well, and there's some other application-specific zk coprocessors. Okay, so in this way, Pico is essentially realizing the so-called glue and the coprocessor architecture proposed by Vitalik last year. So whenever a user is interacting with Pico as a glue point, which already integrates the function level coprocessor, it's able to handle the general logic inside the Pico itself, but also for application-specific logics, it is able to utilize all the existing zk coprocessors to achieve the best performance. Right? So as a showcase, we have shown here that by integrating a Pico with a zk coprocessor, we can get a pretty good performance compared to just using Pico. So the task here is to prove the trading volume of 4096 trades on Uniswap. It is very important for them to do this because they want to issue some kind of rewards to the user which has traded a lot. And then if we just write a plain Rust using the plain Pico, it will cost us like 10,000 seconds to actually do the proof, whole proof, end to end. And then if we are going to be integrating coprocessor with the Pico, then we can just use 300 seconds to do that. And this shows actually more than 30 times acceleration. And then it's not only that, it's also a 2/3 of the code cost. Right? So yeah, we are very happy with that. And then this is actually the very beginning of us integrating with many application-specific circuits. And we are hopefully to integrate more of them in the future. Right? So we are Brevis. Welcome to Build with Pico. Thank you.
Thank you very much, Alan.